raw material that is in Bio 160. So you've already learned about cell respiration, photosynthesis, and you've already learned about these topics as well. So it is largely a review, but you know, there's a little bit added detail, of course, as with everything else with 211. So for the start of this, you all are familiar with energy. What is our definition that you've learned many times in chemistry classes? What is energy defined as? So, yeah, yeah. Anybody have a working definition in their head of energy? Yeah.
It's what's required to do work.
Yeah, it's the ability to do work. So exactly, the capacity to do work or the ability to do work. In this class, largely we're going to talk about Gibbs free energy. That's really the term we will be referring to, and that is the letter G. We use the letter G for Gibbs. And free energy is the energy in a system that is available to do work. So it's energy that we can harness, that we can use for work. Now, this picture right here, I don't know if anybody recognizes where this is taken. It's waterfall, yes, for sure. Anybody been to this waterfall? Yeah?
It's in
Oregon.
It's in Oregon, yes. This is Multnomah Falls. Anybody ever been there?
last year.
Yeah, I actually spent my whole childhood, like my teenage years, my dad he lived across the river on the Washington side, but every year during the summer I worked in the lodge there as a bus girl, and then I was like a waitress for years in the little lodge. So anyway, I recommend visiting this if you ever get over to the Oregon Columbia River Gorge area. The reason I show this is because a waterfall is a perfect example of the two types of energy. So what are the two types of energy that we have? Kinetic and potential, right? So at the top of that waterfall, you have potential energy, which is stored energy. As a water molecule moves over the edge, it's going to become, that energy is converted into kinetic energy. So broadly, those are the two types of energy that we talk about in this class. Kinetic is movement, right? So kinetic energy is the energy of movement in a system. Lots of different ways you can see kinetic energy. So heat is an example. And heat, if I click on this, it's basically these balls that are vibrating off of each other. That shows what heat actually is. It's sort of collisions of molecules. Electromagnetic radiation would be the energy of light. If you think about the electromagnetic spectrum, it goes from the visible light spectrum, but we even have things on there like X-rays, infrared, radio waves, cell phone waves, right? All of those are found along the electromagnetic radiation, but all of those would be energy of motion. And then potential energy is stored. So in this class, we primarily talk about chemical potential energy, which is basically energy in a bond. We already said that when we are forming a bond, we have to put that energy in so that it can be stored. And then we will look at several examples of electrochemical potential energy, which is when you have a gradient and you have a separation. In this case, it's electric because it's a separation of charges, and it's chemical because we have a gradient of concentration. So in this case, we have a proton gradient. We will talk about proton gradients in the mitochondria and also in the chloroplast. Those are used in cell respiration and in photosynthesis. Okay, so one concept we're going to talk a lot about is how do we know how much potential energy is in a bond? And to figure that out, we look at how reduced or oxidized the bond is. So we have to kind of come back to that concept of oxidation and reduction. Okay, so it turns out that if the electrons that are being shared in a chemical bond are pretty equally shared, that bond has more potential energy. So along this spectrum, I have a carbon-hydrogen bond shown at the left. That, you see the electrons, they're right in the middle. So would that be a polar or a non-polar bond if the electrons are shared equally? Non-polar, right? So the more non-polar bonds you have, those electrons are essentially available to either atom. And so that means there is more potential energy. Carbon-carbon and carbon-hydrogen bonds have the most potential energy. We also say that they're the most reduced. So those bonds are reduced. As you go to the right here, I have a nitrogen-hydrogen bond and also an oxygen-hydrogen bond. What's happening to the electrons in the middle?
They're shifting towards the electronegative zone.
Yeah, they're moving towards the more electronegative atom. So nitrogen is more electronegative than hydrogen, and oxygen is very electronegative. So it's hogging the electrons. Because those are unequally shared, the electron density is less available. And so we say that has less potential energy. So the more oxygen we add to a compound, the less potential energy there is. We also say that this is more oxidized, right? The more oxygen is present there. So for this relationship here, if the shared electrons are far from the positive charges in both nuclei, that would be the case of this one. We say the bond has greater potential energy or higher potential energy. If the shared electrons are held closely by one, as in this example, the bond has less or lower potential energy. Okay, so that's sort of the concept of oxidation reduction. If you look, I took this, I always like to go back to these are like relics now. This is my textbook from when I went to college. Was Albert's. They were in the 4th edition back then. We're way farther along now. But I like this picture because it shows kind of what's happening with electron density. Here we have atom 1 and atom 2. They form a polar covalent bond. So they're sharing electrons, but polar tells us that they're sharing unequally. Which one of these has a stronger pull on the electrons? Is it atom 1 or atom 2? Which one has greater electron density around it? 2. So this atom is gaining electrons, is holding on to electrons. So we would say, let's see, if a polar bond is formed and one of the atoms has a stronger pull on the electrons, it is going to be, what would you say, the oxidized or the reduced? If it has the electrons. It's the reduced. That atom would be the reduced atom. This one would be the oxidized atom. So if you want an easy way to remember, a lot of you have learned oil rig. So oxidation is losing electrons and reduction is gaining electrons. That's kind of an easy way to remember, where the electrons are is the reduced atom. Okay, and then just to kind of go through, this picture again, taken from this edition of the textbook, what I like about this picture is it shows what's happening as you have oxidation. So if you look at the electron density around carbon, it's showing you how much electron density is available to carbon. In a methane molecule, where you have all 4 carbon-hydrogen bonds, there's a lot of electron density available. So this has high potential energy. As I start to add oxygen, you can see this circle around the carbon is getting smaller. So there's less electron density available, and it's less potential energy. So methanol has less. If you add a double bond, that's getting even smaller. And here you have formic acid, so 2 oxygens, and you've got a double bond, even smaller. The most oxidized we have is carbon dioxide. Very tiny. There's not a lot of electron density available to the carbon. So that sort of explains, as oxidation occurs, there's less and less potential energy available. So for CH4, would we say that is the most oxidized or the most reduced molecule? We would say the most reduced, so this blank should be reduced. And CO2 would be the most oxidized. Which one would have the most potential energy? Methane or carbon dioxide? Methane. Methane, the more reduced it is, remember, the more potential energy it has. Okay, so on this, all right, well I guess, this just shows essentially the same idea turning the oxidation ladder this way. Now that's methane and it moves all the way to carbon dioxide this way. and also shows you the potential energy ladder as well. If we think about our foods that we consume, so if you think about macros that people consume, we have fats, carbs, proteins, right? Which of those foods do you think provides you the most potential energy?
Fats.
What do you?
Fats.
So yeah, this is a fatty acid, this is a carbohydrate, and then anyway, these are not actually, I don't have an amino acid shown here, but anybody know? So somebody said fat, somebody said carb. It's actually fats that have the most kilocalories per gram, and that's because if you look at the fatty acids, they have a lot of carbon-carbon bonds and carbon-hydrogen bonds, so they have the potential to pack more energy. And then fat per gram, I think it's 9 kilocalories per gram of fat, and it's 4 per gram of carb or per gram of protein. So you can see when we go to carbohydrate, we've added oxygens, that's becoming more oxidized, still can contain energy. We know that carbohydrates are great sources of quick energy, but it's less than what our fats can give us. Okay, so one thing you notice, as things become more oxidized, you see more oxygens. Another thing to kind of look at is substances that have more hydrogens, because hydrogens come with, you have the proton itself and it comes with a pair of electrons in that bond. Things that have more hydrogens tend to be more reduced. So I guess we got 2 minutes left. The last thing we can do in class is just look at number 3 here. There's pairs of molecules, and I want you to circle the one that is more oxidized in the pair. So there's 4 different pairs. For each one, you have to pick which thing you think is more oxidized, which thing is, and then you figure out which one is more reduced. And if you don't, this is NAD plus and NADH, if you want to look at the actual picture of what NAD plus and NADH look like.
I was gonna say, I think.
Is it